there's a wonderful book about why some kids struggle with math. And Steve has a chapter in it. He's got a bunch of papers as well. But what's the biggest predictor of kids struggling with fractions? Concepts. They don't understand what fractions are, and they're not paying attention. I'm going to talk about both of those. As they go further, it's like the kids don't have math facts, then they really are beat down when it comes to equivalence. It's really hard to see thirds and twelfths and make them the same denominator if you don't know your math facts. But even baser than that, dealing with just unit fractions. Kids don't have fraction concepts, they can't do it. It's not about procedure, it's about understanding what it's about. So how do we know fractions? How do we learn fractions? I'm going to talk about 3 different ways. One is that we may actually have an innate fraction sense. We have a lot of informal experiences that kids bring to school, and then there's the formal instruction. So what do I mean by innate fraction sense? Well, we're born to do math. I don't care what anybody says, it's like, I'm just not good at math. We are all born with a mathematical capacity. We can do things like subitize. People know what subitization is? The ability to recognize a quantity without counting. You can look at that and go 3. Now, not only can people do this, but pretty much all mammals can do this. And there was a study recently with honeybees, that honeybees are able to do this as well. It's very interesting how they figure out that honeybees know that that's 3, because they don't have a name for 3. But they have these different, they attune them, they do this stuff. Chimps are actually better at subitizing than humans. On a BBC site, you can actually play Beat the Chimp. And they've got the same mechanism they used with the chimps to see where they hit a bar when they match quantities and stuff like this. But we're able to do this. Mammals were able to do this. We can recognize quantities 1, 2, 3, even up to 4, 5, chimps up to 6 without counting. That's a mathematical ability. We can compare. That's really, can you guys see the blue in there too? I can't, I'm colorblind, so it's really, I don't know, I can barely see it. But this, there's yellow and blue, although I have no idea what colors those are in the real thing. On here, it's yellow and blue. And so we're able to make a comparison. We're able to say at a quick glance, which is more, yellow or blue? And nobody has to teach us to do that. It's a very helpful ability from an evolutionary perspective, because you're looking and saying, how many of them are there versus us? Should we stay and fight or run away? And so making those kind of comparisons are something that happens all the time in the animal kingdom. And so we do this, and actually as the ratio gets closer to 1 to 1, it's harder, right? It's real easy to tell the difference between 12 and 80. It's a lot harder to tell the difference between 59 and 62. But people who are good at it, and there's a huge variability here, but people who are good at it, they did a test of 6th graders, and 6th graders who were good at telling which was greater when the ratio got close to 1 to 1, that was an incredibly high predictor of their past and future academic success in math. The kids who were good at that in 6th grade had a history of success in math, and when they went through high school, those were kids who were successful in high school. I'm not saying it's a cause and effect thing, but it's an interesting correlation, and it's something we are able to do. We're all able to do that bit of math as we're born. We can even add and subtract. There's like a 2-year-old with a binky here, or 1.5-year-old at best, maybe 12, 18 months, with all these electrodes on his head and little puppets over here. There's a place at Harvard called the Baby Lab, and where they do this kind of thing. And they take infants and they test them and say, what kind of math can they do? And kids who are newborns can add and subtract. They can tell the difference between 1, 2, and 3. If you have 3 and you take away 2, they know there should be 1. And they do this with puppets, and they measure their surprise. And if there are 3, and they take away 2, and they have these curtain that goes up, and there's 1, that's like, okay. And if there's 3, and they take away 2, and they raise the curtain, and there's 2 there, they go, wait a minute, that's not right. So they're able to know. And again, they've done this with animals. We can add and subtract at some level without any, we're born with this ability. And there's all this geometric ability that we have, spatial sense that we have. There's even a notion that we can recognize fractions at birth. And they've done some interesting tests where they take and they use ratios to familiarize young kids with a fractional relationship or a ratio and see if they're able to recognize those. And say, oh no, I know that's the same fraction, that's a different fraction, to see those relationships. So there are some indicators of even a fraction ability. There was a study recently, notation-independent representation of fractions in the human parietal cortex, which is interesting for those who like this stuff, in the Journal of Neuroscience in April. And there's implications for mathematical education. I wouldn't go too far with this. This was a study of 12 right-handed Germans. So I'm not sure I would leap to, now we need to change the way we teach fractions. We all know how the brain works, because we don't know that it works with left-handers, for instance. But there's a growing body of knowledge about kind of the capacities that we bring to math, that our kids bring with them to math, even in fractions. A fair bit we know about whole numbers. We're getting a growing knowledge about fractions. But it shouldn't be that the kids have some capacity. We have some capacity. And then that capacity, we build on that with our informal experiences. We share. And that gives us a sense of parts of a whole and fraction relationships. So parts of a whole, we see that very concretely with sets and with continuous quantity. Anybody who has a sibling knows about sharing and has a pretty good sense about an even split. And when I was little and my brother and I shared a bed, we had a line down the middle of the bed. That was my side, this was his side. And he was older, so sometimes his side was a little bigger than mine. So a little more than half. So we have this informal knowledge that we bring with us that's actually pretty robust. We see ratios in our life, and kids, of course, see lots of percents. They see ratios and percents often in their grades. You got 9 out of 10, you got 8 out of 10, you got 80%. So kids are not blank slates when it comes to fractions. They have a lot of informal and intuitive knowledge that they're bringing into the classroom. And then often we screw it up. What do we do? There are a lot of problems with typical instruction. I'm not saying your instruction, but I'm saying a lot of instruction in the US, there are problems with it. One problem is we load kids up with all the definitions of a fraction. It's a measure, right? It's like, we have a measuring stick. You guys know this. It's on a ruler. It's a measure. It's a ratio. It's a comparison of two different things. Well, actually, it's a division. But it's also part of a whole, so you've got, and it's part of a whole with sets, and it's part of a whole with continuous quantity. And of course, when you use fractions as a multiplier, it's the same thing as a percent. And it's like, whoa. That's a lot. And for kids who are struggling to begin with, so what is it? What am I supposed to do with it? And we have a problem with doing too much at once. We often treat fractions as a separate number system. We do whole numbers on a number line. Great, got it. And it's like, now we're doing fractions. Now we're in pizzas. And kids do not see the connection. There's great research out there that fractions are its own number system, whole numbers are a different system, and when we do decimals as point something, we really screw them up, like 0.12. What's that? That's not this system, that's not that system, that's a whole other system. So we are not creating this as a whole for kids, so to speak. And when you go to other countries, high-performing countries, and you ask them about fractions, they have all kinds of models to pull from. You read Li-Ping Ma's book or any of the research that's on high-performing countries, and they have so many different ways for talking about fractions. We have one. And I'm not talking just about kids, but you talk to teachers too, and it all falls back to pizzas. That's how we start. And I like pizza. It's yummy, it's good, it's familiar. But it doesn't lend itself to a holistic understanding of a number system that includes whole numbers and fractions and decimals.